This conference will now be recorded.
Hello everyone. So the topic that we are going to discuss today, gas laws and kinetic theory. That is, we will try to see how we can correlate the gas laws that we have discussed with the kinetic theory that we have finished in the last class. Then Maxwell-Boltzmann distribution of speed of molecules of gas and kinetic energy of gas molecules. There will be some terms using which we can solve problems. Fine. So gas laws and kinetic theory. So different gas laws we have already done. For example, Boyle's law, Charles' law, Gay-Lussac's law, etc. So the first that we are going to discuss is the link between pressure and number of moles. So how we can find the link? But by applying kinetic theory. Okay. So the pressure of a gas that results because of the collision between the gas particles with the walls of the container. So if gas particles are present in any container, so suppose these are the particles, so when there will be collision with the wall of the container, then pressure will arise. Now each time a gas particle hits the wall, that means it is exerting a force. Fine. So it means when there is increase in number of gas particles in the container, obviously the number of collision with the walls of the container, that will also increase. So it means that directly the pressure is related to the number of moles of gas molecules present in the container. So there is a link between P pressure and N, that is number of moles. Fine. Next we'll see Boyle's law, that is pressure. We know that it is inversely proportional to 1 by V, but how we can describe it or explain it on the basis of kinetic theory, that we will see now. So this relationship we already know. Now when we compress a gas, that means we are increasing pressure without changing the temperature. So that is the condition of Boyle's law. That is, if you want to see what is the relationship between pressure and volume, obviously you have to keep temperature fixed. Fine. So under that condition, the average kinetic energy of gas particles stays the same, because average kinetic energy, that is actually related to only temperature. So when you are fixing the temperature, obviously you are also fixing the average kinetic energy. Now our kinetic energy details the terms, why it is only related to temperature, that we will also see in today's class. Right now just see, when you are fixing temperature, average kinetic energy is also fixed. Now you are compressing the gas. So what will happen? There is no change in the speed with which particles move. But now the container is smaller because we are compressing it. Fine. Now that is volume is compared to initial state, now the volume is less. But speed, if you consider for the gas particles, there is no change because temperature is fixed. And when temperature is fixed, kinetic energy is fixed, that means speed will also remain same. Thus the gas particles travels from one end of the container to the other in a shorter period of time. So speed is same, but now the space available, that is decreased because we have decreased the volume. So now what will happen? The particle from one end of the container to the other, suppose if this is the container, this is the distance from one corner to another corner. Now as we have decreased the volume, so obviously this distance is less compared to previous state, but speed is same. So what will happen? Obviously now it will hit the wall more often. The frequency of hitting the wall, that will increase because now time is shorter. So now when frequency of collision with the walls of the container is increasing, that means it is also related to increase in pressure. So see how you have reached the same conclusion that we have already seen in case of Boyle's law. According to Boyle's law, we know that pressure is inversely related to volume. That means you are decreasing volume, so pressure will increase. But we can also explain it on the basis of the postulates of kinetic theory, right? So in this way, we can say that the pressure of a gas, that will become larger when the volume of the gas smaller compared to initial state. Next we will see Gay-Lussac's law, which is pressure related to temperature. How this that is directly related to temperature, this relationship that we can explain on the basis of kinetic theory. When we are increasing temperature, suppose initial state temperature is having one value and now you are increasing the temperature. So obviously average kinetic energy of the gas particles that will increase because it is dependent only on temperature. Fine. So temperature increased, kinetic energy increased. So now the gas particles as kinetic energy is increased, the gas is now warmer also because we have increased the temperature. Now under this condition, mass of these particles constant, because when we are trying to see the relationship between pressure and temperature, obviously we have to keep the amount of gas constant and also volume constant. Fine. Then only you can compare the relationship between, that is, you can understand the relationship between pressure and temperature. So because the mass of these particles constant, their kinetic energy can only increase if the average velocity of the particles increases. So kinetic energy increased because we have increased the temperature. So average velocity of the particles, that will also increase. That means now the particles are moving faster compared to the state when temperature is low. And when they are moving faster, that means they will collide with the wall of the container. And collision increasing means, that is, collision with the wall of the container means pressure is also high. So now they will exert a greater force on the wall of the container. Since the force per collision becomes larger as we are increasing the temperature, so obviously it means pressure is also increased. So in this way you can reach the conclusion that is pressure is directly related to temperature. Temperature increase, pressure increase. Temperature decrease, pressure is decreased. So this is actually nothing but Gay-Lussac's law that we have already seen in Gay-Lussac's law, but that is observation. That it is observed for in general for all the gases. It is observed that when you have kept volume constant, amount constant, then pressure and temperature, these two are directly related to each other. But that is observation. But what is the explanation? What is the reason behind it? That you can understand only from these postulates of kinetic theory, right? Next is V related to number of moles. So volume related to number of moles, that is directly related. That is actually Avogadro's hypothesis. But we will now explain it on the basis of kinetic theory. As the number of gas particles increases, or it is, you can also say that number of moles increases. It is same thing because per mole there is a fixed number of molecules, which is Avogadro number. So whether you say gas particles increasing or whether you say number of moles increasing, it is same thing. So when n value is increasing, the frequency of collision with the walls of the container obviously will increase because now the number of particles are high. Amount is constant, temperature is constant, pressure is also constant because you are comparing the relationship between volume and amount of gas. Sorry, amount of gas is not constant because we are just trying to see the relationship between volume and amount of gas. Amount of gas means number of moles of gas or number of gas molecules. So when we are trying to see the relationship between V and N, obviously we have to keep pressure, temperature constant. So under this condition, when you are, that is, increasing the number of gas particles, obviously collision with the walls of the container must increase. Now this in turn leads to an increase in pressure of the gas. Now if it is flexible containers such as balloon, because it is elastic in nature, it will expand until the pressure of the gas inside the balloon once again balances the pressure of the gas outside. Now it is true that we have fixed the pressure and temperature, but when you are increasing the number of gas particles, there will be a tendency to increase in pressure, but pressure cannot be increased because that we have to keep fixed. Now to balance it, that is, there is increase in pressure, but they should not be increased. So to balance it, as there is a flexibility in the container, so obviously to balance that, that is basically outside pressure and inside pressure of the container, that will, until that is reached, then there will be expansion in the container because it is flexible in nature. So it will continue until the outside pressure, inside pressure, they are same. Until that point, it will continue. So now we can say that the volume of the gas, it is proportional to the number of gas particles. So as you have increased the number of gas particles, so volume will increase. And this is Avogadro's hypothesis. Charles law. Charles law is relationship between volume and temperature under the condition that you have kept pressure fixed and amount of gas, that is number of moles fixed. Then only we can understand the relationship between volume and temperature. So average kinetic energy of the particles in a gas, that is proportional to temperature. Fine. Now mass of these gas particles constant because we are comparing V and T. So when mass of the particles constant, the particles must move faster because now you have made the gas warmer compared to initial state. How you have done so? You have increased the temperature. So temperature increased, average kinetic energy increased. So obviously the speed of the particles will increase. Okay, so now they are moving faster. So particles will exert a greater force on the container whenever they are hitting the walls. Now that will lead to increase in pressure. But remember, pressure must be constant because we are comparing V and T. So it is the same type of situation in the previous slide that you have seen, that you are trying to see the relation between V and N, Avogadro's hypothesis. You are increasing number of moles, but pressure is increased, but we have to keep the pressure same. So to do that, volume will increase. But in this case, it is reverse. But what is happening now? That the particles are exerting a greater force. That means there is increase in pressure. But pressure, that will have to keep fixed. So the walls of the container, they are now flexible, just like before, as we have seen. So as the walls of the container are flexible, there will be a tendency to expand. Until what point? Until the pressure of the gas once more balances the pressure of the atmosphere. Because outside pressure, that is fixed. Under fixed pressure, we are comparing V and T. But whenever you are increasing temperature, there will be a tendency to increase in pressure. But that should not be, we cannot increase the pressure. So to balance that, to nullify that effect, the container, because of its flexible nature, it will now expand. So what conclusion we can reach? That volume of the gas therefore becomes larger as the temperature of the gas increases. So it is nothing but that it is saying that the relationship between volume and temperature, it is actually directly proportional to each other. So we are reaching the same conclusion that we have already learned in case of Charles law, but that is observation. But now you can understand what is the real explanation behind that based on kinetic theory. Kinetic theory of gases, it proves only Boyle's law, only Charles law, only Avogadro's law, all of these. So just we have finished and we have seen that it is based on kinetic theory. Not only Charles law, that is already present in this slide, but we can also prove Boyle's law, that is the relationship between P and V, inverse relationship, P is inverse related to 1 by V. Charles law, that you can already see here, and only Avogadro's law. Avogadro's law hypothesis also we have just finished in the previous slide. So that also you can explain based on kinetic theory. So basically all these three you can explain, right? So which option will be correct? It is the last option. That is all of these laws we can prove on the basis of kinetic theory. So correct option will be this one. So after finishing this relationship between, that is correlation of gas laws and kinetic theory, next topic is Maxwell-Boltzmann distribution of speed. So now you will be able to understand that how the speed in the previous 3 to 4 slides, what we have seen, that when temperature is increased, average kinetic energy is increased and speed of the molecules also increased. Now you will actually see how the speed of the particles of the gas molecules, how it is related to temperature. What is the effect that you can see the graph. So we will see some graph. As we have assumed that molecules of a gas have different speed. So that we have already seen in the last class. That is a postulates of kinetic theory. So suppose in gas particles there are 100 molecules. Arbitrarily I am just saying. So it is not necessary that all of them will have same speed. So different speed will be there. It is necessary to know how many molecules may possess a speed of a given magnitude. So it is true that 100 particles, suppose it is present in a particular continent, and all these particles are having different speed. It may be that some particles are having, there is a group of particles having same speed. Suppose 5 particles are having fixed speed, or 10 particles are having some fixed speed. So it may happen. Now, if it is so, it is important for us to know that how many molecules, suppose 100 molecules, but out of 100, how many molecules are having a particular speed. That is, if you want to know that out of 100, how many molecules are having speed x. Okay, so if we want to know that, then we have to see the relationship, that is how the speed is increasing with temperature, and that also in terms of fraction of molecules. So here the graph that you will see, in the y-axis there will be fraction of molecules. So see here what is mentioned, fraction of molecules. So this is the value, that means if it is I am saying 0.3, that means 3 by 10. So out of 10, 3 molecules will be having this speed. So as we are increasing the scale, so fraction of molecules out of total number of molecules, that will also increase. And in the x-axis we have velocity. Fine. So suppose I am just arbitrarily choosing this point. So if I am drawing 2 lines on x-axis and y-axis, so this is a value somewhere, suppose it is 400. So 400 velocity, that is 400 meter per second. This velocity will be for this fraction of molecules. So there will be a particular value, suppose x fraction. So x fraction of molecules will be having speed 400 meter per second. Okay, so in this way you can understand how the fraction of molecules that is changing with increase in velocity. So relationship between fraction of molecules and velocity. Now here total 4 lines you can see, right? So this is for nitrogen molecule. So 4 lines. What is the difference between these 4 lines? This is 100 Kelvin, 200, 500, 1000. So that means gradually you are increasing the temperature. Now when you are increasing the temperature, what change you are seeing? First look at the graph which is for 100 Kelvin. So at 100 Kelvin, this is the peak point. That means if you draw a line here, this fraction, this value of fraction of molecules, that will be having speed at this point, which is around 250. Arbitrarily I am just saying. Now when you have increased the temperature, nature of the graph is more or less same. It is like this hump type of curve. That is fine. But what is the difference now you are observing? The difference is, here this is the peak point. Now when you have increased the temperature 200, now the peak point is this one. Okay. And if you draw a line, now the fraction of molecules having highest speed, because for each temperature category, first category 100 Kelvin, second category 200. So for each temperature category, this is the point where maximum fraction of molecules are present. Okay. So when you have increased the temperature to 100 Kelvin, this is the fraction of molecules that will be having speed. Suppose somewhere here it may be 400, 450 or something like this. Okay. Now from 200 further, when we are increasing the temperature, here these graphs are gradually flattening, isn't it? So sharpness is decreasing, it is gradually flattening. It is better I say broadening. So now this is the peak point, and this is the fraction of molecules corresponding if I draw a line, and the velocity is here. And this is the point. If you draw a line, fraction of molecules, and velocity is somewhere 500. So suppose this is 550 like this, and this is 900 or so, arbitrarily. Now the important point that you have to understand, when you are increasing the temperature 100 to 200, 200 to 500, 500 to 1000, the fraction of molecules is decreasing. This point, this one, and this one. So fraction of molecules having this, that is a peak point if you consider for all these four graphs, that fraction of molecules is decreasing. Okay, so that we can understand from this graph. So here, speed distribution curve broadens when you are increasing temperature. Now it means that the fraction of molecules moving at higher speed, that will increase. So as it is broadening, that means the graphs are shifting from left to right as you are increasing the temperature. Now when you are increasing the temperature and it is shifting from left to right, that means now you are gradually moving towards 1000 or 1500 like this, starting from 0, because it is moving towards left to right, it is broadening. So when it is broadening, obviously the fraction of molecules moving at higher speed, that will increase. Okay, it is true that the, if you consider the peak point, that is this corresponding velocity, obviously that fraction is decreasing, but here the statement that is mentioned, that is different. It is saying that the fraction of molecules moving at higher speed, that means when we are increasing the temperature, most of the molecules will try to move at higher speed, and that is expected, because if it is related to temp, basically this is observation, and from observation we can draw some conclusion. So if this is the observation that with increase in temperature, fraction of molecules having higher speed increasing, it means it has direct relationship with temperature, right? So when temperature is increased, velocity is also increasing. That is, most of the molecules are now moving with higher speed with increasing temperature. So Maxwell and Boltzmann, they have shown this distribution of speed in a gas at a certain temperature. So fraction of molecules, how it is, that is having different velocity. So some molecules are having low velocity, some molecules are having high velocity. But you can compare these two, that is, you can get the relationship between fraction of molecules and velocity only when you have kept the temperature constant. Then only you can compare. Because you can see here, when you are increasing the temperature, the nature of the curve is also changing. So only at particular temperature, at a certain temperature, you can show the distribution of speed in a gas for all the molecules. So it depends in a certain temperature, because it depends on temperature. And not only temperature, it also depends on molecular mass of the gas. So these 2 points important. So that is why here we have taken only nitrogen, because if you take some different gas, obviously the nature, there will be some change, because it is also dependent on the molar mass of the gas. So in this graph you can understand from these 4 different temperature how the curves are changing their nature. And next, if you look at this graph, where again the fraction of molecules that is present in the y-axis, here it is mentioned having speed v, but whatever it is, this v may vary. And we have velocity in the x-axis, and we obviously we have to keep temperature constant, because if you are not keeping it constant, it will also show its effect. So when temperature is constant, then you can understand from these 2 different gases. So here mass is different, okay, and here it is 32 molar mass. Hydrogen, it is 2. So here molar mass is less for hydrogen, and for oxygen it is high. So you can see the nature of the curves are completely different, okay, provided temperature is fixed. So at the same temperature, lighter gas. So in our case, hydrogen is lighter gas. It will have higher value of most probable speed. Now, most probable speed means that we are going to see in the next slide. This speed we are talking about. So why we are saying this peak point speed? That is, if you consider this peak point and maxima, if you draw a line on the velocity axis, this is the value of corresponding velocity. So this fraction of molecules will be having this velocity. Suppose this is x. And if you consider the maximum for the hydrogen line, you are drawing a line over velocity, you are getting another value of velocity, and suppose that is y. Now y is obviously greater than x. That is clear from the graph, right? So it means what? When your gas is having less molar mass, that is a lighter gas, that will be having higher value of most probable velocity, because this velocity which is present at the maxima point, that velocity is called most probable velocity. Why most probable? Because this is the point where it is reaching the maximum fraction of molecules. So for this green line, which is oxygen, this is the point where you can have max value of fraction of molecules, isn't it? And if you consider hydrogen, this is the point when you have max fraction of molecules. So it means what? Now this is the velocity which is acquired by maximum fraction of molecules, and that is why it is the most probable velocity. So for very in a simplistic way, if I say, suppose there are 100 molecules, and out of 100 molecules, suppose 70% molecules are having a particular speed. Though it is oversimplification, but try to understand. Suppose most of the particles. So better I say 60% or 65% or 55%, because it is more than 50%. So most of the percentage of molecules, the corresponding velocity, that is actually the most probable velocity. Most probable in the sense because maximum fraction of molecules are having this velocity. Okay. So this graph that you have just seen, it shows that the number of molecules possessing very high speed and very low speed is very small. Why it is saying so? Because the nature of the graph more or less is like this. That means this is the zone where velocity is low. This is the zone where velocity is high, right? But these two zones, the corresponding fraction of molecules are less. But if you consider this max point, which is intermediate velocity, this is low velocity, this is high velocity. So if you are somewhere here, obviously this is the in-between velocity. Now this in-between velocity, the corresponding number of molecules, that is actually high. So that is why it is saying that the graph shows that number of molecules that are having very high speed, very low speed, that fraction is actually very small. But the most probable velocity, the corresponding fraction, that is actually high. This is one point. Second point is total area underneath this Maxwell-Boltzmann speed distribution curve. That is actually equal to total number of molecules. So this total area means you have to just consider this total area. So it will give you the total number of molecules. Now here you can see three different terms. All these three different terms are very important. So this peak point, this is actually most probable velocity. Sometimes it is it is mentioned with CMP, most probable, or it can be mentioned with V, most probable. Here it is written as P, but it is actually most probable. P for probable. So it can be expressed by C or V, or it can be also expressed by U. So different books you can find different terms, but whatever it is, it means most probable speed, and its value is found to be root over 2kT by m. Now T is temperature. Okay, m is the mass of single molecule. M is small m. Be very careful when I am using small m, that is actually mass of single atom or molecule. In general, I am saying single particle. And this K is basically called Boltzmann constant. It is expressed as small k. It is not capital K, it is small k. And that is actually equal to universal gas constant divided by Avogadro number. Remember this relationship? Boltzmann constant, that is equal to R by Na. And small m is mass of single particle. So small m, that you can say that that is also equal to capital M divided by Avogadro number. What is capital M? Capital M is mass of 1 mole. So 1 mole gas particles, the corresponding mass is capital M, which is called molar mass. When you are dividing it by Avogadro number 6.022 or 3 into 10 to the power 23, these numbers, that means for these numbers the corresponding mass is capital M. So for one particle the mass should be capital M by Na, and that is nothing but small m. Okay, so this is the relationship between small m and capital M and Boltzmann constant and universal gas constant R. So here most probable velocity, it is this point, the maximum point, the corresponding value. This is in green color. Now there are two more terms. One is known as V average, that is average velocity, and that is equal to root over 8 kt by pi m. And there is a third term which is known as root mean square velocity or speed. Now what it that is actually means, we'll see in the next slide, but right now you just have to remember these three formulas for most probable velocity, for average velocity, and root mean square velocity. These three are in there. And remember, these three can also be expressed in terms of, suppose in place of k, if you write that is this k by m ratio, it is actually equal to R by m. How? Because k is equal to R by Na and small m is equal to capital M by Na. So Na is cancelled. So it is actually equal to R by m. So if it is true, then Vp you can also express it like this, 2 RT by capital M. So this is also true. So if we write all this in terms of universal gas constant and mass, molar mass, then it will look like this. So Vp, or I am writing here most probable velocity, that is equal to 2 RT by M. Then V average, that is equal to 8 RT by pi M, and root mean square, what it actually means I will show. Right now just see the terms and you have to remember all these terms. Now one question which is very common is that if it is said that what is the ratio of these three, VMP, V average, VRMS, how we will do so? So you just have to take the ratio of these three. Now in these three terms, what terms are common? Just try to find. So here RT by M, this part is common. So just cancel it. Now you are remaining with root 2, root over 8 by pi, and root 3. Now if you take, that is if you simplify, if you take the actual value, you will see that finally you will reach this ratio, 1 is to 1.128 is to, so this is the ratio of these three velocity terms. So from this, what conclusion you can draw? That here this is actually maximum, after that this one, and then this one, and that you can also see from the graph. So if this is cutting here, that is the x-axis. If it is cutting here, then this is a blue line, this is a green line. So obviously this point is higher than this and this, because when you are moving from left to right, velocity is increased. But remember this ratio, because based on this you can get problem. So here it is mentioned, that is K is Boltzmann constant, which is equal to R by NA, and if you divide R by taking this value 8.314, that is SI unit, and divide by 6.022 into 10 to the power 23, which is Avogadro number, you will get this value of Boltzmann constant, which is 1.38066 into 10 to the power minus 23. See, this power, it will be now minus, and unit is joule per Kelvin. R is the universal gas constant. So if K is equal to R by NA, obviously R is equal to Kn, and this is the R value. Next, we'll see how we can understand the root mean square velocity, because average velocity, what it means, that you know. Simply take the average. Most probable velocity, that is also clear, because the most fraction of molecules, the corresponding velocity is called most probable. But what is root mean square velocity, that we will see now. So kinetic energy, it is actually half mu square. So suppose u is a particular value of speed. When I'm saying average translation kinetic energy, that is linear movement, translation kinetic energy, average term we are using, then there is a mu bar sign. Okay. So this bar sign, it means mean of square of speed of all the molecules. Now mean of square of speed of all the molecules means, suppose there are different velocity, u1, u2, u3, all put a bar sign. That means mean of square of speed of, sorry, not bar sign here. So as there is a large collection of molecules, so suppose there are different velocities, u1, u2, u3, dot dot up to un. Now under this condition, if we consider this term, that is u1, just take square of all the terms, then add all this, divide it by L, which is the total number of particles. So if you do so, then you will get this mu bar square, which is mean square speed, that is mean of square of speed of all molecules, that is this mu bar square. Sorry, this square. And it is a direct measure of average kinetic energy of gas molecules. So when you take this mu bar square and if you put it here, half m mu bar square, that will give you the kinetic energy. Okay. So the square root of mean of square of speed, that is actually known as root mean square speed. Now it is not same as most probable speed, it is not same as average speed, that you have already seen. Different terms we have used. So when you take root of this mu bar square, then you get this VRMS, or sometimes it is written as CRMS. Okay, but this subscript RMS, it means the full form is root mean square. Okay. So here we have a problem. One graph is given in the question, and here 3 different points are marked with a dotted line which has cut the v, that is speed, which is in x-axis. So this is the, it is nothing but most probable velocity, that you can understand, vmp, where it has touched this v axis, that is speed axis, x-axis. So these three different speed value. So points 1, 2, 3 in the following plot respectively correspond to, now look at these 4 options. All these are VMP, but 3 different gases are mentioned in the question, right? So what are these 3 gases? We have oxygen, we have nitrogen, we have H2. Here that is 1, 2, 3 respectively. That means whether 1 is corresponding to O2 or N2 or H2, 2 is corresponding to O2, N2, H2, that you have to find. So here, if you just consider option 1, O2 is present at first position. That means this should be 1. This is 2 respectively mentioned, and this is 3. Now for oxygen, it is always 400 in the bracket mentioned. See? And for hydrogen, it is always 300 mentioned. For nitrogen also it is 300. That means for nitrogen and hydrogen, the temperature is 300. But for oxygen, it is 400. Different, right? Now, most probable velocity, what is the formula? Remember, it is root over 2RT by m, or in terms of Boltzmann constant, you can consider 2kT by small m. But most of the time, you will see that 2RT by capital M, it will be more important, because when it is capital M, molar mass you can easily calculate. Single mass, if you want to know, then again you have to divide it by Avogadro. So better you use the term 2RT by M. So if you are using this, that is VMP is equal to this value, it means it is directly related to the root over value of T by M, because R is constant. So I can also write it is directly related to T by M. Now why we are doing so? Because you have to calculate this T by M for each of these 3 gases. So for oxygen, the M value is 32. For nitrogen, the molar mass is 28. For hydrogen, it is 2. Oxygen, it is 32, 16 plus 16. Nitrogen, it is 14 plus 14. And for hydrogen, it's 1 plus 1. All are diatomic. And for oxygen, how we will calculate this T by M ratio? It will be 400 divided by 32. See, 400 divided by 32. For nitrogen, it will be 300 divided by 28. And for hydrogen also, it is proportional to 300 by 2. Now, if you simplify all these, you will see that is the different values that you will get. You can simplify that without using calculator also. You can understand when it is 400 by 32. If we that is divided by 100, it will be 108, or I can say it is 25 by 2, which is around 12.5, right? For nitrogen, it is 300 by 28. That means you can change it to, if you divide each by 4, it will be 75, 7. Now this is almost equal to 10.7. And for hydrogen, it is simple 150. So what conclusion now you can draw? You can draw the conclusion that this is max, root over 150. This is obviously max. After that, this one, then this one. So first, that is V and P, which is 3 is max, then 2, then 1. So 3 should be for H2, the middle one should be for O2, and then it should be for N2. So in the question it is mentioned 1, 2, 3 respectively. That means N2 first, then O2, then H2. And that you can find in which option? N2 first you can find in option 2 and 4. So these two cancelled. But in option 2 and 4, what is the difference? After N2, second position is hydrogen. Here second position oxygen. But second position should be oxygen. So this is also cancelled. So you are now left with only this option. Okay. So the first most probable velocity, point number 1, that is minimum value. It is root over 10.7. So it is corresponding to 1. Then that is middle one is 12, root over 12.5, which is matching with that is corresponds to 2. And the last one for hydrogen is corresponding to 3. Okay. This is one. Last option, correct. Which one of the following statements is not true? That means you have to find a false statement, and the statements are related to it is about the effect of increase in temperature on the distribution of molecular speed. So it is nothing but Maxwell-Boltzmann speed distribution curve related problem. Okay, so just remember how the curve looks. It is something like this: fraction of molecules y-axis, speed in the x-axis. We have taken three different temperature. You can take any temperature T1, T2, T3, where T1 is less, then T2, then T3. So with increase in temperature, the nature of the curve is that it gradually flattens or broadens. Look at the first statement. It is saying that the most probable velocity increases when there is increase in temperature. Because look at the question, carefully read. It is asking about the effect of increase in temperature. That means when you are shifting from 0 to 1000, not necessarily 0 to 1000. Here I have just taken this picture. It may be 0 to 50, 60 also. So when you are increasing the temperature, then is this true that most probable speed increases? Yes, it is true, because this is the most probable velocity. The corresponding, if you draw a line, it will cut here. When it is 1000, it is cutting here. When it is 2000, it is cutting. So obviously this is true. This cannot be correct option. Next statement is the fraction of molecules with most probable speed increases. Now you have to consider most probable speed. That means fraction of molecules with most probable speed. So when it is temperature 0, this is the most probable speed. This is the corresponding fraction of molecules. Suppose this point is x. This is most probable velocity at 1000. The corresponding line, if you draw, it is y. When it is 2000, the corresponding line, it will cut here. So suppose this is z. Now you can easily understand, in the fraction of molecules, x is greater than y is greater than z. That means fraction of molecules with increase in temperature is basically decreasing, not increasing. So this is the term which is not correct. So that is why this should be the correct option. It is false. Now how the other two statements are correct? Because we have already reached our correct option. The distribution becomes broader. That is very easy to understand, right? And the last point, the area under the distribution curve remains the same as under the law. So whatever your temperature, this total area, suppose you are considering the red line, this is the total area. Next you are considering the green line, there will be some different total area. When you are considering the 2000, there will be a different total area. But whatever it is always same. And that point is already mentioned when I have discussed Maxwell-Boltzmann distribution. So fraction of molecules with most probable speed decreases, not increases. So this is not true. Total area under the curve is not dependent on temperature, because total area means total number of molecules, and that you can understand, it will not change with temperature. It will always remain same. So it is independent of temperature, and that is the reason the area under the distribution curve represent that is total number of molecules, and that cannot be changed with temperature. Okay, so 3 and 4 both are correct. Correct option, option 2. Now we will use, that is, we will see some terms. Derivation we will not do, that is not required, but to solve question you should have some idea about some terms, and that we are going to see now. So here you can see this PV product, P into V, that is equal to 1 by 3 small m, then capital N, then root mean square velocity. Now what square of root mean square velocity? Now what is this m and n? So this m and n basically P and V pressure volume. M is mass of a single particle, a single molecule. N is total number of molecules, available total molecules, and this is root mean square velocity. Now this PV, this term 1 by 3 mn c square RMS, you can make a slight change. Suppose you are writing this 1 by 3 like this. Now you are writing 2 by 3 into 1 by 2, which is another way of writing 1 by 3, because 2 will be cancelled, but you are writing it in this way. Now this 2 by 3 and this m, suppose you have taken these two terms and now you have written it here. Now you are left with half m c square RMS, which you have written here. Now this half m c square RMS, that is equal to epsilon. Just like E, but there is a difference. It is written like this. It is known as epsilon. So PV is equal to 1 by 3 MNC RMS square, or you can also write that it is equal to 2 by 3 N epsilon. So why these formulas are important? Because suppose in some question these MN values are given and or PV given, and you have to find C RMS square, or basically there are total 5 terms. So out of 5 terms, if 4 terms are known, obviously the unknown you can calculate from this formula. Similarly, this E epsilon value you can calculate provided you know P, V and M. Now this epsilon, you can call it, it is average energy per molecule. Okay. Now there are these other terms also. So this is average energy per molecule, and this is also equal to 3 by 2 kT. Remember, K is Boltzmann constant, which is nothing but R by Na. You can also write it like this. So these are the different terms. Depending on what type of problem you are getting, you have to use it accordingly. So epsilon, it is related to PV by this relationship, PV equal to 2 by 3 N epsilon, or epsilon is related to temperature. In this relationship, you can see epsilon is equal to 3 by 2 kT. And what is the this capital E? Capital E is, this is also average energy, but now this is not per molecule, this is per mole. That is the difference. So when you are saying average energy per mole, it is capital E, and that is equal to 3 by 2 RT, universal gas constant, no Boltzmann gas constant. But when it is epsilon, which is average energy per molecule, this is per mole, this is per molecule, then you have to consider 3 by 2 kT. Now under this condition, suppose this capital N, total number of molecules, if it is somehow equal to Avogadro number, then you can write this equation, PV equal to 2 by 3 Na into epsilon. Okay. Now Na into epsilon is basically capital E, because if Na into epsilon is capital E, because see, epsilon is energy per molecule for a single particle. So when you have Avogadro number of particles and you are multiplying it, so obviously Avogadro means number of particles in 1 mole. So number of particles in 1 mole, and now you are multiplying it with it, average energy per molecule. So obviously it will be equal to energy, average energy per mole. So PV is equal to 2 by 3 Na into epsilon, or PV is equal to 2 by 3 into E. Okay, so these are the different relationship that you can use, provided what type of values are given, for which term the values are given. So here different terms you can see how PV is related. So this is one, the first one. Then PV, how it is related to epsilon, which is average energy per molecule. Then also how PV is related to average energy per mole. PV is equal to 2 by 3 E. Then look at these two, how capital E is related to temperature, how epsilon is related to temperature. Fine. So these, all these, try to, you have to remember. So we are at the end of the session. Thank you for listening.